So in this example, a bullet initially traveling at 350 meters per second strikes a concrete wall and penetrates 25 centimeters before coming to rest. So if I were to try and sketch this just a little bit, so we've got our concrete wall and we have some object that was able to poke through the surface and then come to a stop. So it doesn't specify which direction that bullet was heading, so I've just drawn it going to the right. And so I'm going to assign that rightward direction positive. So anything that's headed leftward would be a negative value. So I'm expecting that. If I go through and I read this, bullet initially traveling at 350 meters per second, well, that's an initial speed, 350. Strikes a concrete wall and penetrates 25 centimeters before coming to rest. So the distance it covers then is 0.25 meters. And if it comes to rest, then that means its final speed is 0. So I'm missing the time and I'm missing the acceleration. So if the thing was traveling this way and its speed is decreasing, that means it's being pushed backwards. So I'm expecting the acceleration to be negative. Time is, of course, never negative unless you've got some sort of thing that happened in the past. So I'm expecting to get a negative value for my acceleration despite all of my inputs being positive. So I guess we just calculate it and see what happens. So an equation connecting initial speed, final speed, distance, and acceleration would be this one. Vf squared minus vi squared is twice acceleration times the distance. V final is 0. V initial is 350. 2a. And the distance is 0.25. So 0 squared is gone. I'm gonna write that in here for a second. 350 squared is 122,500, and 2 times 0.25 is 0.5. Now this here, you notice that it wasn't negative 350 squared. It was the final speed subtract the initial speed squared. So I have to do 0 minus 122,500, which gives me negative 122,500. So that negative persists there. So just be careful with your algebra. To move this, I have to divide both sides by 0.5. If I do that, that should give me my acceleration value. And this number divided by 0.5 is negative 245,000 meters per second squared. That's very aggressive, but we are talking about a bullet slamming into a concrete wall, so that's probably not untoward. All right, so we need to get the time that it takes for this to happen. Oh, note, negative acceleration as expected. So an equation that connects initial speed, final speed, distance, and time would be twice the distance is Vf plus Vi t. So 2 times 0.25 is a final speed of 0 plus 350 multiplied by t. 2 times 0.25 is 0.5. 0 plus 350 is 350. And divide both sides by 350. Time ends up being 0.5 divided by 350. 0.00143. Which is 1.5 milliseconds. Which that seems about right for a bullet slamming into something. So we've got our remaining kinematics variables have been solved. 2, 4, 5, 0, 0, 0. And t is 0.00143 seconds. So we need to get the power output, the change in energy, and the force applied to this bullet. And I'm noticing that I've neglected to put in mass here, so let's put in there a 50-gram bullet. So switching to calculating energy, energy at start would be EK is 1/2 mv squared. Would be 1/2. 50 grams in kilograms is 0.05 kilograms. Initial speed was 350, which gives us a grand total of 350 squared times 0.05 divided by 2 is 3062.5 joules. Okay, the energy at the end, EK is 1/2 mv squared, but our final speed is 0, so that's going to end up being 0, which makes our change in energy, the energy at the end minus the energy at the start, and I get negative 3062.5 joules. Now, negative energy, that's a funny result. Anything we've done so far where we had a slower speed initially and then a faster speed at the end had positive changes in energy, which meant that the kinetic energy increased. Here the kinetic energy decreased. That's a little different. In the previous examples where the kinetic energy was increasing, we had to ask ourselves where that energy came from. So it either came from a fuel source, if it was a car, or etc. If the energy is negative, instead of asking how the energy got in, we're now asking how the energy got out. So if you're a bullet slamming into a concrete wall, there's going to be some friction. So there'll be heat loss due to that. That's one way of losing the energy. There'll be some kinetic energy imparted to the wall as bits of it fly away, or the wall itself pushes the millimeter or so that it might reflect. So that's why this is negative, is that this kinetic energy has left the system and become something else. Pop that in there, delta E. It's negative 3062.5 joules. So the power rating then would be minus 3062.5 divided by 0.00143, which equals divided by 0.00143, 2,141,608.391. So that's 2.14 megawatts. So this kind of energy loss is on the order of megawatts, which is crazy, because that's that's what wind turbines run at as far as electrical output goes. So that's kind of scary. Pop that in here. 2.14 megawatts. And the last thing would be the force, mass times acceleration, which is 0.05 times that really scary number, negative 245,000, giving us a total of 5 times 245, 1, 2, 3 zeros, 12,250 newtons. So there's a number of negatives that popped up here. So the first place it showed up was in the acceleration. So this thing's speed was being changed that way. So it started going 350 meters per second in this direction, and as this process unfolded, it was being pushed that way, pushed back, like in resisting its attempt to go through the wall. So you can see that here, the energy has to come out, right? The bullet was full of energy at the beginning, and it is not full of energy at the end, so all this had to be dumped into the surroundings. And then the force is negative, so that's again, the push was in the leftward direction, trying to bring that bullet to a rest as it tried to force itself through the wall. So when dealing with kinematics questions where suddenly we have the idea of up and down involved, you have to establish a framework for what things are positive and what things are negative. So generally, when doing a question, like a vertical type question, because we have a grasshopper leaping upward and then falling under gravity, generally we choose upward motions as positive and any downward quantities as negative. So I'm gonna pop that up here, that up is positive. So if I go through these variables then, I have 5 grams. So my mass is 5 grams, which happens to be 0.005 kilograms. And I have a 10 centimeter dandelion. So if and you have your flower, I guess that's what a dandelion could look like. If the flower is 10 centimeters and this grasshopper makes a mighty leap upwards and then lands on the ground later, the net distance it's traveled is 10 centimeters below where it started. So since I've decided that upward distances are positive, if this grasshopper is now 10 centimeters lower than where it started, I need to use a negative. So the distance at the end is going to be negative 10 centimeters, which is negative 0.1 meters. Lovely. Now this phrase, falls to the ground. So you could make this complicated and throw in some air resistance, etc. But just to keep things easy, anytime something is falling, so free falling, right? It leaps and then it lands somewhere else without spreading its wings or doing anything complicated. You may assume that it's accelerating under Earth's gravity. So the acceleration due to gravity near the surface of the Earth is negative 9.8 meters per second squared. And I am using the negative because gravity is pulling you downwards. So I have a positive mass, a negative distance, a negative acceleration, and I need a time in there. So let's and falls to the ground, landing 2 seconds later. So I have a time now. Oops. Time of 2 seconds. So if I can get my cartoon off here. I, as always, need to find the remaining 2 kinematics variables as well as the force required to make this motion happen and the change in energy from the start position to the final position for power output. So if I have distance, acceleration, and time, I'm missing the final speed. I'm missing the initial speed. And I still need force, and I still need power. So I need an equation that connects final speed with time, acceleration, and distance. So I have this one. Distance is VFT minus 1/2 a t squared. So a distance of negative 0.1 meters, v final, which I don't know yet. Time is 2 seconds, minus 1/2, an acceleration of negative 9.8, and a time of 2 seconds. So negative 0.1 is 2v finals. A negative times a negative is a positive, and half of 9.8 is 4.9. 2 squared is 4. Negative 0.1 is 2v final. 4 times 4.9, 19.6. I'm going to have to subtract this from both sides. I'm going to subtract this over here. Negative 0.1 minus 19.6 is 2v final. So negative 0.1 minus 19.6 would be minus 19.7. And if I divide both sides by 2, I end up with 19.7 divided by 2, 9.85. Now, a handy way to check to see that if you've done everything correctly is when the grasshopper leaps upwards and then falls downwards, the final speed should be negative because it is heading downward. And we decided up there that positive quantities meant up. So if the thing is dropping, then its final speed should be negative, and that's what we ended up with. So that's good. We can pop that in there. Negative 9.85. I'm going to clear this up so we can do initial speed. So I need an equation that combines distance, acceleration, and time with initial speed. So that would be distance is initial speed time plus 1/2 a t squared. So using my distance of negative 0.1, an initial speed I don't know about, 2 seconds worth of time, an acceleration of 9.8 downwards, and a time of 2 seconds. Negative 0.1 is 2 initial speed. Now a positive times a negative gives me a negative answer. Half of 9.8 is 4.9. 2 squared is 4. And I have already forgotten what 4 times 4.9 is. 19.6. So I'm going to have to add this to the other side. So negative 0.1 plus 19.6 is 2v initial. That ends up being 19.5 is 2v initial. So divide both sides by 2. Initial speed ends up being 19.5 divided by 2, 9.75 meters per second. So this particular grasshopper leapt upwards from the dandelion. So again, we should check this number against our reference frame. It came out positive, and we've decided that upward actions were positive numbers. So in the text of the question, it does say that the grasshopper leaps this way. So that's good. It has leapt upwards because this is positive. So I can just pop that in there. All worked out. All right. Force, as always, is mass times acceleration. So in this particular question, I had a 5 kilogram grasshopper, or 5 grams, so that's 0.05 kilograms. acceleration of negative 9.8. Force is 0.00005 times 9.8 negative is negative 0.049 newtons. Now, I have a negative there, so to interpret that, that means that the force causing this acceleration, this acceleration should be pointed downwards because it's a negative number. So I'm going to pop that in there. Negative 0.049 newtons. And to do my powers, I need to do the energy calculations. So energy, kinetic energy, 1/2 mv squared. If I do the initial energy first, I have 0.005 kilograms and an initial speed of 9.75 meters per second squared, which gives me 9.75 squared is 95.0625 times 0.005 is 0.4753 divided by 2 is 0.2377 if I round joules. So if I do the end energy, 1/2, mass is still 0.005, and the final speed is negative 9.85 squared. Now, a negative number squared is just a positive. So I have 9.85 negative squared multiplied by 0.005 divided by 2 is 0.2426 joules if I round. So my power output then would be the energy at the end, 0.2426, subtract the energy at the beginning, 0.2377, divided by the amount of time it takes, which we calculate, or we were given as 2 seconds. So 0.2426 minus 0.2377 is 0.0049, and divide that by 2. I get 0.00245 watts. And if you're a fan of metric prefixes, you could write that as 2.45 milliwatts. Let me pop that in there. There you go. Okay, a new example. You throw a 100-gram ball of paper into the wind at 5 meters per second. The wind accelerates the ball at 1.5 meters per second squared for 6 seconds. So I maybe gave the game away there by putting a negative on it. But if I try to draw this little scenario, I mean, here's you. Here's the ball of paper going this way, and the wind is heading in that direction, because it does say that you're throwing it into the wind. So I have some opposing directions here. The ball's initial speed is heading that way, and the wind is going that way. So one of these things has to be negative. Either the initial speed or the acceleration has to be negative. I'm just going to choose to make the initial speed positive for no reason other than I happen to have drawn it headed to the right. So if I choose rightward as the positive direction, then my initial speed is 5 meters per second to the right. My acceleration, because I threw the ball into the wind, the acceleration is the other way, 1.5 meters per second squared to the left, and I'm going to show left by using a negative. And I have a time here of 6 seconds. So I'm expecting my final speed. It's possible that after 6 seconds that the thing hasn't quite slowed down yet. So if my final speed is positive, it is still heading rightward. So the wind hasn't turned it around yet. If my final speed is negative, it means that the ball has gone into the wind, come to a rest, and headed back to the left. So I'm not sure yet until I do the calculations, but I could get either, depending on if this is enough time for this acceleration to reduce this speed to 0. As far as distance is concerned, I might get a positive number, I might get a negative number. Since the experiment started where this little stick man is standing, if the ball is in front of that person 6 seconds later, then my distance will be positive. If the ball is behind this person 6 seconds later, my distance will be negative. At this point, I don't know. I have to do the problem and see how it works out. So I need an equation to connect initial speed, acceleration, and time to distance. So that's this one. Distance is what I'm calculating. Initial speed is 5. Time is 6. Acceleration is negative 1.5. Time is 6. 5 times 6 is 30. Half of negative 1.5 would be negative 0.75. And 6 squared is 36. 0.75 times 36 is 27. So the distance is 3. Now that's a positive 3. So this ball, that doesn't mean that it's traveled 3 meters in total. It means that its position from the start point is positive 3 meters, and positive means rightward in this question. So this particular paper ball was thrown into the wind, and then it came back, and 6 seconds after it was thrown, it is located 3 meters to the right of the individual who threw it. So we need to get our final speed. So I'm still not sure whether final speed will be positive or negative. If it's still heading that way when it's 3 meters out, then I'll have positive. If it has gone out and come back, then I would have a negative. So let's see. I need an equation for VI, VF, A, and T. So VF minus VI is acceleration multiplied by time. Final speed I don't know. Initial speed was 5. Acceleration was negative 1.5. Time is 6. 1.5 times 6 is negative 9. Pop this over. VF is negative 9 plus 5. V final is negative 4 meters per second. Alright, so to interpret this person initially threw the ball at 5 meters per second and it headed this way to the right. At some point, it came to a rest and started to head back towards this person. 6 seconds after it was thrown, it is headed to the left at 4 meters per second and is located 3 meters to the right of where the person threw the ball. So to finish, we just need to do our energy and power. So the energy at the beginning is 1/2 mv squared. It's 1/2, 100 grams in kilograms is 0.1. The initial speed was 5 meters per second. So that's going to give us a total of 5 times 5 is 25 times 0.1 divided by 2 is 1.25. That's not very much compared to the bullet question. At the end, 1/2 mv squared, 1/2, 0.1, final speed is -4. -4 times -4 is 16, times 0.1 divided by 2, 0.8 joules. So the delta energy then would be the energy at the end minus the energy at the beginning. 0.8 minus 1.25 is negative 0.45. So you wonder where that energy has gone. It has less kinetic energy than it had at the beginning. So it's been consumed a little bit by the wind, right? The wind resistance, friction, might be some heat loss. The wind may have moved it around. So this amount of energy has been pulled out. The sort of neat thing about wind, though, is if we let it go, eventually it's going to regain this energy until it finally hits the speed that the wind is traveling at. That's more wind resistance is not a thing we do in this course, so it's a touch more complicated. So power output, delta E over delta T. It accomplishes this change in energy over this amount of time on average, divided by 6. So at that particular moment in time, it is as though this thing was bleeding energy at 0.075 watts. And the force calculation, mass times acceleration, 0.1 multiplied by an acceleration of negative 1.5 gives us negative 0.15 newtons. So at this point, because it's traveling less quickly than it was at the beginning, we've had a loss of kinetic energy, so that's there. So the power rating would look like this. They're both negative because the kinetic energy is being reduced by the wind. Acceleration was negative because we chose to make it leftward in the first place, because we're told that the paper is going into the wind at first. And this negative acceleration resulted in a negative force. Now, so it's negative, which means it's a push in the leftward direction. Okay, so in this particular question, we have a boat. So here we go. Here's your boat on the water. And there's someone in it. Little engine there. So at first, it's heading forwards at 2 meters per second, but throws the engine in reverse in order to avoid hitting the dock. As you know, boats don't have brakes, so you have to use power forward, powered backwards in order to control where it's going. In this particular example, 4 seconds later, it is reversing at 1 meters per second. So one of these numbers is going to be positive. So the initial speed is positive, then the final speed is negative. And it's arbitrary, but I just happen to have drawn this boat going rightward, and it's nice and consistent if you keep to the right as positive all the time. So I have an initial speed of 2 meters per second to the right, and I have a final speed of 1 meter per second to the left, and I'm going to show that it's to the left by using a negative. I have a time of 4 seconds, So I need to work out the distance it travels and the acceleration it experiences. So let's work that out. So an equation connecting initial speed, final speed, and time with distance would be twice the distance is df plus vi multiplied by the time. So 2d would be final speed of -1 plus initial speed of 2 multiplied by the time. 2d is 1 times 4. 1 times 4 is 4. Divide both sides by 2. End up with 2 meters. So where is that? Well, it turned out positive. So that means it's to the right 2 meters of where we started this experiment. So this person is here, and they are now 4 seconds later 2 meters ahead of their initial position. So in order to figure that out, we're going to have to calculate to figure out the acceleration, we're going to have to grab an equation that connects VI, VF, A, and T. So VF minus VI is acceleration multiplied by time. Final speed is -1. Initial speed is 2. Notice that it's minus the initial speed. So subtract +2. Time is 4 seconds. -1 minus 2 is -3. Divide both sides by 4. And I get A is -0.75 meters per second squared. Lovely. Now that should make sense. If the boat was headed this way, and then eventually it's headed that way, then the acceleration has to be in the leftward direction, so that this rightward velocity comes to a stop and then is eventually pushed leftward. So we can calculate our energy and power outputs from this particular boat. So energy at the beginning would be 1/2 mv squared. That's 1/2 of 250 kilograms. Initial speed was 2. Half of 250 is 125. 2 squared is 4. That would be 500 joules. Energy at the end, 1/2 mv squared. 1/2 of the 250 kilograms. Final speed is -1 squared. Half of 250 is 125. Minus 1 squared is 1. So energy at the end is 125 joules. So the change in kinetic energy then would be the energy at the end minus the energy at the beginning, which gives us a value of minus 375 joules. So because it is traveling more slowly at the end of this little exercise, 375 joules of kinetic energy have come out of the system and have to have gone into something else. So the way boats work is the propeller has moved a whole bunch of water. So there's this much kinetic energy has been transferred through that moving other water process out of the boat. So our power output, delta E over delta T, would be minus 375 divided by a time value of 4. So 375 divided by 4 is 93.75 watts. Negative. So we're shedding 93.75 joules of kinetic energy every second. And in order to do the force, I'm going to run out of space here. Force is mass times acceleration. So 250 kilograms multiplied by an acceleration of negative 0.75 gives us a final value of 250 times 0.75 negative is negative 187.5 newtons. So the push that this boat is experiencing is negative, which means the push is in the leftward direction in order to make it come to a stop and then start to reverse.